Hello and welcome to Tech Simplified TV. In our last episode, we have discussed about different aspects of floor planning. Once the top level floor planning is done, the connection between internal and external pins are assigned. Along with that, power and ground lines are routed. In our today's episode, we will discuss about pin assignment and power ground routing. If you are interested, stay tuned and stay focused till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. First, design flow and pin assignment. Next, more on pin assignment. Third, pin assignment using concentric circles. There are 2 slides on it. Concentric circle method is a method to do pin assignment. Another method is in next slide, that is topological pin assignment. This is another method. There are 2 slides on it. Next, we will move to power and ground routing. So, design flow, power and ground routing. Design of a power ground distribution. After that, planar routing. There are 2 slides on it. Mesh routing. There are also 2 slides on this topic. So, these are the topics we will cover in today's episode. We are done with this slide. We will move to the first slide. Design flow and pin assignment. This is the infographic we are using from last episode. Flow planning we have already done. Now comes pin assignment. In chip planning, there are 3 steps: flow planning, pin assignment and power ground routing. In today's episode, we will cover these 2. And first, now we will concentrate on pin assignment. So, design flow and pin assignment. During planning of the layout of large blocks, placement of the connection points, that is terminals, is very important. When we plan larger blocks in the core area, placement of connection points are important because how the connection points are defined, depending on that, the signal line will get routed. And when within limited space, we have to route so many connection line, we have to optimize its position and pin location so that congestion problem can be controlled. Now, these connection points are I/O pins and usually placed on the edges of the blocks to keep the wiring short. Our target is to keep the wiring short, and connections are these pins. Blocks are connected with I/O pins. I/O pins are the channel to communicate with the outer world. Now, I/O pins, in last episode on flow planning, we have shared a diagram, a representative diagram or infographics we have showed where I/O pads are positions on the outer. If you can remember, the best spots for these pins depend on how the blocks are arranged. Position of the blocks are important. Now, during pin assignment, each signal on net is assigned a specific pin location to improve the overall design. This methodology is followed. The main goals are to make sure the wiring is easy to route and to reduce unwanted electrical effects both inside and outside the block. Next, the objective of external pin assignment is to link each incoming or outgoing signal to a unique I/O pin. After assigning each necessary net to its designated pin, the connections must be optimized to minimize wire length and reduce electrical parasitics such as coupling or signal integrity loss. We all know when there is interconnect or metal wiring, these are the associate issues: coupling, signal integrity loss. So we try to keep the length minimum, and to keep the length minimum so that we don't need to route the signal line or power ground line unnecessarily for longer length. Position of block is very important, and pin assignment is important so that it's the starting of the connection from the block to the I/O. So, pin assignment is very important part of chip planning. It's a part of planning. Chip planning, in floor planning, we decide where the blocks are situated, how their shapes are, how much area it will cover, what should be the aspect ratio, as we have discussed in last episode. With all these blocks, they are not isolated. They have to communicate with the outer world so that we can send a signal and get a response. That is the standard method. So now pins, how they are connected. Internal pin to the external pin. In pin assignment, we do that. And later on, we will see that each and every device in a chip, each and every device within a block require power and ground. Otherwise, they are not electrically connected. They are isolated. So every component have to get connected electrically. For that, they must get connection to power and ground. So power and ground is the primary connection. How that signal is routed, that two lines are routed, that is also decided in chip planning phase. So we are done with this slide. We will move to the next slide. More on pin assignment. Pin assignment is used to connect cell pins that are functionally or electrically equivalent, such as during standard cell placement. Two pins are considered functionally or equivalent if swapping them does not alter the design's logic, and they are electrically equivalent or equipotential if they are connected. In pin assignment, we connect cell pins that are functionally or electrically equivalent. When they are connected, they are equivalent or equipotential when they are connected, and functionally equivalent if swapping these two pins doesn't change any kind of logic. If that doesn't create any kind of alteration in the design's logic, then they are equivalent. The primary goal of internal pin assignment for cells is to minimize congestion and reduce interconnect length between cells. Why we do that? So that the congestion, one signal is crossing, another signal is going, that kind of congestion does not arise, and to reduce interconnect length between cells, we do this. And the pin assignment technique described below are applicable to both chip planning and placement stages. These are the diagrams here. So this is functionally equivalent pins, how metal 2, metal 1, this color are there, colored mention. This is metal 2, this red, and these are metal 1 layer, poly layer, diffusion layer is there, now contact, via. These are electrically equivalent pins, and if this is the original design, this is an electrically equivalent pin, this pin and that pin. That's why they're connected, and this pin and that pin. Here, now if we swap, if we change their position, so that, look, this connection, and here we simplify it. How? Now, this is moved to here, so that directly connected to here, like that. And once this connection is shifted here, this is shifted to there, this position, and swapped. So, this is connected to this one. So next it will be like that. Here it's simplified. This connection is much more simplified. It was crossing each other. Now here it's not like that. Similarly, these and these are equivalent, and now these two are equivalent. So if we swap, so this is simplified. No one is crossing another one. There is no crossing of signal lines. They are not crossing. Wiring are not crossing each other. So this way we swap position, simplify the connectivity. We are done with this slide. We will move to the next slide. Pin assignment using concentric circles. This is a methodology. This algorithm connects a block to all its associate pins in other block with minimum cross connections. It operates under assumption that all outer pins have fixed positions. Inner pins are positions based on location of their electrically equivalent outer pin. The algorithm employs two concentric circles. That's why the name is concentric circles method. The inner circle for the pins of the block being considered, and the outer circle for pins of the other blocks. The primary goal is to assign valid pin location on both circles without no net overlap. So if that is the block, inside block, these are the pins and these are the outer pins. So we consider one, first determine the circles. We consider a circle like that. Between these two column of pins, the maximum possible circle we are drawing here, and another one is another concentric circle we are drawing like that only. So two circles are drawn such a way that all pins that belong to the blocks are outside the inner circle and all external pins are outside the outer circle. So within these two columns of pins, the maximum place we are utilizing. Similarly like that. And now determine the points. For each point, draw, this point is done. Now for each point, draw a line from that point to the center of the circle. This was the original line. We are drawing a line to center. This is the center of the circle. We are drawing a line this way. So that the line connecting this pin position of the pins and the center, there is a line and that crosses the perimeter of the circle. Similarly, we do for the outer circle also. Okay, and then move each outer point to the where line meets the outer circle and move each inner point to where the line meets the inner circle. So there is a point. So we are shifting two sets of pins, their positions. We are shifting like that. So now these pins positions are shifted on the circle perimeters in both cases. This is the second step. We are done with this slide. We will move to the third step on next slide. Third point is determine initial mapping. The initial setup pairs each outer pin with a matching inner pin, like that only. We are mapping this to that. Similarly, like we can do it in one direction only. We are going clockwise, like that, this way. We have pointed like this. Start by choosing any pin and assign it to an inner pin. Then assign the rest of the pins either in clockwise or anti-clockwise direction. Connection this way. Either we are moving from this way to that or this way to that. Now optimizing the mapping. Repeat the process of pairing outer and inner in different ways. Start with the same outer pin but try pairing with different inner points and then pair the rest of the point accordingly. Continue until all possible pairings have been tried. The best pairing is the one that has shortest total distance between the points. In this problem, an example pairing is shown on the right. At left, the best pairing is in the center and final pin assignment are on the right. We can start from any point and can move to keep on connecting. So we will get different set of connections and the best one is which has the shortest. So we are just moving like that and the shortest one we will take, the minimum. And this way from here we are taking this, that is the shortest one. Now we replace again this circle with the block here, the block and their pins. So that connection is like that. Because this point was, we draw it, we just bring it from the pin of the block, inner block. Now we are replacing with the original points and now this is the best connection. This is one method. This is concentric circle method. So we are done with this method. Now we will see the next method. Topological pin assignment. This algorithm is an improvement to concentric circle pin assignment algorithm. It takes into account external block positions and multi-pin nets. This allowed pin assignment even when external pins are behind other blocks. So there has some benefit over the previous algorithm. So this is the inner circle or this is the inner block. Main component is M and B is the external block. This is the main internal block and this is the external block. A midpoint line LMB is drawn from center of M through the midpoint of B. This is the center of M and this is midpoint of B. We are drawing a straight line like that. Another line we draw, that is this one, in between B and M like that so that it intersects the LMB. Pins of B are unwrapped and expanded as line L dash at the dividing point D. Further point in the LMB that intersections B. The pins are then projected onto outer circle. So we draw a line L dash like that and this way this pin is like that. We project pins of B like that, this way. We are projecting and from there we are drawing lines to the center of this M like that. We are projecting, first we project these points on this line, these pin positions on this line and then projecting on the circuits up to this, like this only. We are done with this slide and let's see what we do next in the next slide. So that is in last slide what we see, that is for one block. Now this method allows multiple blocks to be considered simultaneously. There are two blocks A and B. On block A, consider the midpoint lines LMA and LMB. Two lines are there, LMA and LMB. Two lines we are drawing like that only in from midpoint. And if this is the position, the midpoint D1 is formed this way because it is the further point LMA. This is D1. This is the D2 is formed because it's closer point on LMB and D3 is formed because it is the further point on LMB. This way, D1, D2, D3, this way we are selecting the points and using D1 to D3, the pins are unwrapped. What we would do? We would do unwrapping first from D1 to D2. So if that is D1 and D2, then these are the pins 1, 2, 3 and these are A1, A2 and A3. Look from D1 to D2, A1, A2, A3. Next D3, this is D3. After that D2 to D3, D3 to D3. So D3 to D3 means these all will come under it. So that is B1, B2, B3, B4, B5, B6, B7, B8. B1, B2, B3, B4, B5, B6, B7, B8. And now after that this comes like D2 to DA. We are done up to this point. Now D2 to D1. So D2 to D1 means this pins. That is A4, A5, A6, A7, AA. A4, A5, A6, A7, AA. This way. They are projected on this inner circle. So this circle, these are projected. So that is topological pin assignment. We are done with this slide. We will move to the next slide. Now we will see power and ground routing. Again, this diagram, this is power and ground routing. So chip planning involves designing the power ground distribution network and positioning supply I/O pads or bumps. Up to 20 to 40% of all metal resources on the chip are used to supply power, VDD and ground nets because these are the most long interconnects. Every cell needs electrical connection. If VDD and ground are not connected, then those cells are isolated. So these are the longest wiring paths. And the power planning process includes iterative steps such as early simulation of major power dissipation components, initial estimation of overall chip power, analysis of total chip power and peak power density, examination of total chip power fluctuation, analysis of inherent and additional fluctuations causing by clock gating, early analysis of power distribution including average, maximum and multi-cycle fluctuation. These are power planning methods and these steps are done early and these are very iterative steps. Iterative steps to get close to the best result. We are done with this slide. We will move to the next slide. So design of a power ground distribution. Every cell needs both VDD and ground connection. They connect each cell in the design to a power source. VDD and ground supply lines are large, cover entire chip and are routed before any signal lines. Core supply lines differ from I/O supply lines which usually have higher voltage. Single core power line and core ground line are usually enough, although for some ICs like mixed signal or low power design, we may have multiple power and ground lines. Low power design we have discussed about in our power management series that in low power design, sometimes we use multiple powers for multiple segments of the chip just to optimize the power. Not all portion of the chip requires same kind of power. So for that multiple power supply system is used. This is referring to that only. Routing power and ground lines is different from routing signal lines. Power ground lines require their own metal layers to avoid taking up space needed for signal routing. Now, thicker metal layers, typically top 2 in the manufacturing process, are preferred for power and ground lines due to their lower resistance. They run for the longer length. To keep resistance low, thicker metal layers are used. When power ground networks spans multiple layers, sufficient vias must be used to carry current and prevent reliability issues like electromigration. Supply lines carry high current, so they are often much wider than signal line. The width of each wire segment can be adjusted based on expected current, that is calculated based on current. Wider segments have lower resistance, which reduce voltage drop. There are two main approaches to designing power ground distribution. One is planar approach and another one is mesh approach. The planar approach is used in analog or custom blocks and mesh approach more common in digital ICs. So these are two methods, planar approach and mesh approach. And this is basically about the power lines, why they are wider. Thicker metal layers are used. If power ground network spans multiple layers, sufficient vias must be used to carry current and prevent reliability issues like electromigration. Electromigration may happen because it's heavy current flows. Electromigration is a common reliability issue. We have discussed it multiple times. Sufficient vias must use to avoid electromigration situation. We are done with this slide. We will move to the next slide. Planar routing. The power supply nets can be routed using planar routing when only two supply nets are present in the design. A cell needs a connection to both supply nets. A Hamiltonian path is created that connects all the cells. What is Hamiltonian path? You will see that. The path divides the layout in two regions, one for each supply net. That's a path. It's such that in one side of this path is VDD, another side is ground. Look, it's connecting all the blocks in such a way that on right side VDD and on left side it's ground. Each supply net is routed either the left or right side of the path for each cell. So both supply nets can be laid out without conflicts across the design. Routing the power and ground nets in the planar fashion can be accomplished with following 3 steps. Planarize the topology of nets. Since both power and ground nets must be routed on the same layer, the design should be divided using a Hamiltonian path. Start routing the power and ground nets from the left and right side, respectively. Ensure both nets expanded in tree-like structure, avoiding overlap and maintaining separation by Hamiltonian path. The precise routing will depend on the pin location. This way, Hamiltonian path is dividing the whole design into 2 sides. One VDD, here ground. They are connected to each block, although in between Hamiltonian path is going. So this way connection is going on each side. We are done with this slide. We will move to the next slide. Now, layer assignment. Net segments are allocated to specific routing layers considering factors such as routability, the resistance and capacitance characteristic of each available layer, and design rule constraint. How much current will go through that layer, that calculations and everything like resistance, capacitance, all values are calculated and depending on the layers are assigned. Determining the width of the net segment. The width of each segment is based on maximum current it needs to carry. This width is determined by summing up currents from all connected cells according to KCL. For large currents, designers often increase the width by stacking multiple layers vertically connected by vias. Deciding right width is usually an iterative process because currents are influenced by timing and noise, which are in turn affected by voltage drops, creating a cyclic dependency. This loop is typically resolved through multiple iterations and expertise of experienced designers. After completing these steps, the power ground segments are adjusted to avoid obstacles during general signal routing. This is iterative method, and for large current, designers often increase the width by stacking the multiple layers vertically and connected by vias. This way they design it. What should be the right width? That is an iterative process because currents are influenced by timing and noise. Noise is there, timing limitation is there. In turn, that affect voltage drop, creating a cyclic dependence, and experienced designers solve these kind of issues. We are done with this slide. Now we will move to the next slide. Mesh routing. This is another method. Power ground routing in state-of-art ICs has mesh topology. These are 5 steps followed to create the topology, creating a ring. A ring is placed around the main part of the chip and sometimes around certain sections. Its role is to connect the power supply and electrostatic discharge protection to the chip's power network. To reduce resistance, this connection and ring are spread over several metal layers. For example, ring might use metal layers from metal 2 to metal 8 but skip metal 1. This is power rail. This is ring, pad, base, all connections, and this is the closer view. Connecting IO pads to the ring. The image shows how IO pads are connected to the ring. Each IO pad has several metal layers with many small extension, fingers-like structure. These extensions should be connected to the power ring as much as possible to lower resistance and improve the flow of the current to the core. Now, creating mesh. A power mesh consists of stripes placed at set distances across 2 or more layers. The width and spacing of these stripes are based on the expected power, use, and design rule. The stripes alternate in pairs like VDD ground, and so on. The upper and thicker layers are mainly used for power mesh, while the lower layers have fewer stripes to avoid blocking signal path. Stripes on nearby layers are connected with many vias to resistance. How this mesh structure is done, that is described in these steps. So first is create a ring, then connect IO pads to the ring, and then creating a mesh. After that, creating metal 1 rails. The metal 1 layer is where the power ground network connects to the logic gates of the design. Metal 1 to metal 4 connection is showing here. Metal 1 VDD rail, ground rail, then this is a via metal 2, here via metal 2, again via metal 3, now metal 4 mesh. From 4 mesh started. So the width and spacing of metal 1 rails, which determine how much current can be supplied, are usually set by standard cell library. The standard cell rows are placed back to back, allowing the power supply to be shared between 2 neighboring cells rows. This is done. This back to back connection is done for ease of connectivity. Now connecting the metal 1 rail to mesh. Lastly, metal 1 rails are connected to the power mesh using stacked vias. These stacked vias, it's important to choose the right size of the via stack, that is number of vias in it. Ideally, most resistive part of the power distribution should be the metal 1 segment between the via stacks, not the stack themselves. The via stack is also designed to maintain flexibility in routing. And from metal 2 to metal stack, metal 4 connection like that, metal 4 via 4, metal 5 via 5, metal 6 this way, and then metal 8, 6 to 8. This way connection, metal layers and then vias, metal layers and vias, these way connections are developed. So this is mesh routing. We are done with this slide and we are done with our today's topic, where we have covered pin assignment and power and ground routing. Thank you for watching up to this point. Don't forget to like, share and subscribe. In case you have any dislike, please put it as a comment. If you have a query or question, also put it as a comment. Thank you again and bye for today.